Hi everyone. Today I'm going to discuss a few examples of sensors which is designed to measure distance or range or identify an object. So I'm going to start with this ultrasonic range module, which is HC-SR04. So according to this data sheet, so the module is something looks like this. Is very familiar for anyone who is working with robotics or embedded system designs. So it has a transmitter denoted as T, which is like a speaker, and it has a receiver, which is as a mic. So whatever the ultrasonic signal sent here is hit on an object and reflected back to this receiver. And based on the distance, they will provide a signal. So it has a VCC, which is the positive supply. Typically, we provide 5-volt supply, and this is the ground. And trigger is the trigger signal that you have to send in order to activate this device. And then there's an echo signal, which can be used to identify the range to the object. So the measuring distance, you can measure any distance to an object from ranging from 2 centimeters to 400 centimeters, and accuracy of 3 millimeters. And so the distance, you have to do a little bit of calculation. And this module is 5-volt supply, and it consumes 15 milliamp current and generate a 40 hertz ultrasonic sound. So which is not audible for our naked ear. And maximum distance that it can detect is 4 meters, and the minimum distance is 2 centimeters. If you try to measure any distance less than 2 centimeters, the values are not accurate. And the range is 15 degrees, so your object should be within the range angle of 15 degrees. And the dimensions are 45, 20, and 15 millimeter. And so this is how it works. So you have to provide the 5-volt supply and ground, and trigger and echo should be connected to your microcontroller or any Arduino board. And now we can see here, it has to connected. You should have your microcontroller. So it should drive 2 signals, which is the trigger, and the other one is the echo. That is, this is the input, and this is the output, right? So this should be the this pin of your microcontroller should be connected to the trigger. So here you have to generate a short 10 microsecond pulse, and you have to keep turning it for 10 microseconds and then release. Then this device will generate a 40 kilohertz sound burst. So that will be transmitted through using the transmitter, and once it is received back, so it will generate this kind of echo signal from this the other pin, from this pin, from the echo pin, right? Trigger signal is where you provide that as pulse, and the echo pin is where that's what you are going to use it for finding the distance. So now we can see here, so depending on the distance to the object, like this is your sensor, it has a transmitter T and the receiver R. So you have an obstacle here. So the transmitter will send a signal, and the receiver will get the reflected sound back to here. So like there's a time duration between your transmit time and the receive time, right? And if the distance is large, it takes more time, right? Based on that time duration, so it will generate a this kind of pulse. So this distance, this pulse duration is proportional to the distance to the object. So you have to calculate, you have to measure this pulse duration. Then you can use this equation here. So the range is equals to the high level time, this time, let's say t, simple t, into the velocity of the sound, that is 340 meters per second at temperature is specified. So if you know the temperature, we can search on the internet, like what is the speed of the temperature. So the sound speed changes with the temperature. So you can use an additional temperature sensor, and you can calibrate, like without just putting 340. You can, if you know the temperature, you can make a lookup table, and for each temperature, so there is like a particular value, but it doesn't affect much. I mean, like it does not do much accuracy, but if you wish to have a good accuracy, it's better to come at this temperature coefficient, which is if you know the ambient temperature, and then you exactly substitute this speed of sound at that particular temperature, and it is divided by 2. For example, now if we having let's say like this is it takes 20 microseconds to duration is 20 microseconds, so you can substitute it here. 20 microseconds into the 340 meters per second divided by 2 is the distance to this object, right? This divided by 2 is like from here to here. So this is your reference point, 0 meters, and this is your obstacle, and this is the range that you substitute to this equation t, right? And so you have to work with some coding here. So first you have to generate this square wave signal from your output device, and then the module will generate a 40 kilohertz burst, and when it hits the object and return the sound back, reflect the sound back, so it will generate this pulse. So you have to start a timer. You know, like there are timers in a microcontroller. So you start the timer here, and you stop the timer here, and you can find the timer value from here to here, right? So if the timer value updated with some integer value, so if you know the clock period for each update of your timer, you can calculate this period, right? So you can do it by writing code in NetMelody, or there could be plenty of codings available on the internet for if you use Arduino. Even there could be dedicated libraries for that. So you don't need to deal with much complicated maths and know this activating timers and interrupts if you use Arduino. But if you use FL Studio, you have to work by yourself. There could be some example codes as in the internet as well. And here you have to find out this time period. Then you can substitute this equation and get the distance to the object. So that is how you're going to use this ultrasonic range detector. So which is a very economical version, so you can buy from the market. It is not expensive. It's a cheap one, and it has a good accuracy. Now the next type is using infrared signal, which is this sensor, distance measuring sensor, which is known as JP2Y0A21 A21YK0F. So it can measure distances from 10 centimeters to 8 centimeters. And the output type is not digital, but it is analog. And this is the transmitter where the infrared light is emitted. And this is the receiver. So you have to provide voltage supply within the range of 4.5 to 5.5 maximum, and it typically consumes 30 milliamps of current. And so this is the block diagram. So you have a light emitting IR transmitter LED, and so it is driven by a LED driver, and then this is the IR sensor. So whenever the reflected light hits this sensor, so there's a signal processing unit, and this is where you power the device, and it has an internal voltage regulator to keep fixed voltage here, and there's oscillator circuit, and then based on the distance, there will be output signal comes out from the out. So that is an analog signal. So these are the dimensions, and this is a light emitter. So if you can see, like, this device is working like from your mobile phone. If you turn on the camera and detect focus on this transmitter, you will see there's like a blue color, like a purple color light comes from this transmitter, and this is the receiver side. So supply voltage should not exceed more than 7 volts, and this is the recommended temperature range where you can have the accuracy -10 to +60. So I would try to tell you, like, when you power up the device, when you power up using 5 volt supply, so first measurement, it is unstable, it provides an unstable output. So you have to keep at this, I think, around 50 milliseconds in order to get a reasonable accurate reading. So when you turn on, just don't get the readings, just wait for 50 milliseconds, and then start from the second measurement, and then it will provide the first output. Like, first measurement, I think they are using for calibration purposes and so on. A good accuracy you can ignore the first reading, and it's an unstable output. And from the second, after 50 milliseconds, you can start this getting the data from this device, which provide a reasonable accuracy. And this is the voltage output. So the voltage output from this pin is analog voltage. So you can see, like, this device has this is a pin configuration, and V out is the analog output voltage. So pin number 1 is your V out, pin number 2 is ground, and pin number 3 is the VCC supply. So pin number 1 is where you connect it to your microcontroller, and these are voltage supply. So you have to connect that V out to an analog channel of your microcontroller. And the depending on the distance, the output voltage changes. So you can see, like, so the minimum distance should be 10 centimeters. So you have to keep your, this is your sensor, right? It has a transmitter and the receiver. So you have to keep your object more than 10 centimeters, otherwise it won't work. So any distance more than 10 centimeter can be detected and measured from this device. So at 10 centimeters, you will get a value close to 2.25 volts, and you have to convert into ADC and so on. When the distance increases, so the voltage drops. So the lowest voltage will be around like 0.4 volts at 80 centimeters. So it is like an inverse calculation, which means, like, so what you do is you have to connect your sensor, like this is your microcontroller, and this is V out coming from your IR sensor. So this should be connected to ADC. So you only get the voltage, right? Voltage signal. So depending on the voltage, you have to make this like a lookup table. So you have to use either, if you know exactly know this equation of this graph, you can substitute, but otherwise you can make a lookup table. Like if you know the this voltage, right? So that is what is read from the microcontroller. So you always read the voltage. And if you know the voltage, you have to come back and look at what is the distance from this graph. There's no any specific equation given in this data sheet. All you need to do is either make your own lookup table, or somehow you can derive an equation for this graph and substitute there. If you know the voltage, you can then count the distance. And they also provide like an inverse distance graph, which means if you know the voltage, you will know the inverse distance, which is 1 upon the distance. But you can use this graph, which is more user friendly. So why this it can't detect distance lower than 10? Because you can see like at 10 centimeters, you will get this voltage, which is 2.25, right? And we can see there's another point, like same voltage, there's another reading. So that is not accurate. I mean, like for the same voltage, there are two values of distance. So that's why they are asking you to always follow distances over than 10 centimeters. So when you using this device, you have to be follow several guidelines. First one is you have to clear and clean these surfaces of the transmitter and sensors, like clean dust, water, oil on the surfaces. And so if this sensor is exposed to ambient light, direct sunlight, or tungsten type lamp, the reading might be little bit reading might be deviated from the actual value, and there might be some accuracy issues. So it is always good to use this device for indoor applications. And so if you hit this object to a mirror, so there will be some measurement inaccuracy. And they also recommend, like if you have a boundary, this is your object, right? And you mount your device in a vertical manner, like this is the transmitter and this is the receiver. So it is like a vertical configuration. So mount your device like this. And so now you have a obstacle. So the obstacle has two colors, right? Like this side is red and the other side is blue. And this is the boundary. So this line is the boundary. So in that case, you should not place your boundary in this manner, right? So you have to change either the obstacle or the sensor orientation in order to have the boundary in a vertical, in parallel to your sensor. So now you have the transmitter and receiver, and the boundaries also parallel to your sensor. So this is the correct way. And so if you're having moving objects, like so your sensor is vertical, you have the transmitter and you have the receiver. So the moving object is in this direction. Moving object is in the same direction. So this is how you mounted your sensor, and the moving object either in parallel to your sensor, right? That is not correct. So you have to either keep it vertical. I mean, like sensor, transmitter, receiver in this direction, and the moving object should be in this, either in this direction. So this is the correct way if you want to get a reasonable accurate readings. And so they recommend to use a bypass capacitor 10 microfarad between the VCC and ground. So when you're using this device, you need to just, you can see like there are 3 pins here. VCC and ground is pin number 2 and 3. So they are referring to add a capacitor between pin number 2 and 3. The minimum value is 10 microfarad. So follow that guidelines as well. So then you can use this sensor for measuring distances for most of the time for indoor applications where there are no direct sunlight exposed. But even if you're using in indoor applications, make sure you are not using this sensor is not exposed to tungsten lamps, where we're having a lot of IR sensor emitted. In that case, you can use this sensor for your any application that needs to measure sense distance to a object. Finally, we have this PIR sensor, which is a passive infrared sensor, which is used to identify objects. So they use this device is used to detect motion by measuring the changes in the infrared light level in surrounding area. So this is how it looks like. So it's a 3-pin device. So you have VDG, which is the positive supply, and VSS is the ground. Then you have output terminal, and there's a jumper. Either you can connect it to edge side, or either you can connect to low side. So this sensor is typically used for alarm systems in indoor applications. So in order to detect some theft and so on, if you might have seen this one in the alarm systems in your houses. So this device works with when it is exposed to infrared light, the voltage level of the crystalline material changes, and based on that, they're having a special signal processing unit which convert that signal, and there's onboard amplifier. You can see you have to provide the positive supply within the range of 3.3 to 5 volt, and it consumes only very small current within like 100 microampere. And ground is close to the ground, and output you can connect it to your microcontroller. And so this jumper settings, which I have just shown you here, so either here capital H or low. If you provide capital H, which means like so you have your PIR sensor, and so it takes the ambient IR level. So this is a room, right? So if someone works or any object moves in the visibility of the sensor, so it will trigger. Normally the output pin, right, V out, is normally at 0. So if you set the jumper to capital H, and so it will generate high voltage, and it keeps high until this object is go away from the range, right? And if you use this L mode, so it goes from it goes high when it is triggered, and then low, and so if this object is still there, it will generate like a pulses, square wave pulses, right? And when the object is cleared, it will goes to again back to 0. Here also, when the object is cleared, it will go back to 0. So it is ideal for using indoor alarm systems to detect any intruders. And So if you just turn on the device, so the device takes some time to warm up, which means to calibrate, and it will takes at least 60 seconds, which means like a 1 minute in order to calibrate. During these times, it is recommended to not to have any motion inside a room or the visibility of the sensor. So which means like device needs some time to calibrate the IR level on that particular area. So you have to keep the sensor and turn it on and stay away from it. If you set the device in a particular location in a room. So this sensor has a sensitivity of 20 feet. So within that range, it can identify any changes in the environment. So you don't need to worry about like, the infrared level changes with the time of the day. But this sensor is designed to adjust slowly changing conditions. So which means like during the day, it will recalibrate with the changes on the environment, but it will always generate this kind of trigger signals in for sudden movement within the visibility of this range, right? So they are providing some example codings, but you don't need to much worry about. So if you follow the instruction here, you just need to connect this out pin to your microcontroller, and either if you wish to have a continuous output trigger, you can set it to high. If you want pulsative trigger, pulsative output, you can set it to low. And when there's an object, you will get the output signal as high, and you can use that signal. Make sure when you power just power at the first time, remove any obstacles or any devices within that range for 10 to 60 seconds to warm up. And for slowly changing conditions, it can recalibrate and adjust accordingly. So this device does not provide any range to obstacle or object. Instead, it will provide either 1 or 0, which means if there's a sudden change in the environment, it will set it high. If there's no change, it will always set this line to low. So these are the 3 basic sensors that is used to identify objects, and the ultrasonic and infrared sensors that I have discussed, you can use them for measuring the distance to an object, but this PIR sensor can be used to identify there's an object within that range. So that concludes this obstacles distance measurement sensors and object obstacles identification sensors types, which can be used for your embedded system.